Hello, welcome to the third lecture in our series on mathematical modeling of football. So today we're going to look at simulating matches, and in particular we're going to look at what I think is, you can say, is like the most important mathematical idea behind football, and that's the Poisson distribution. Last week we looked a lot at expected goals, and that's the thing you maybe read about the most as a sort of statistics applied to football. But I think what we're going to cover today, the Poisson distribution, is sort of more fundamental. If you like to think of the idea of mathematics underlying things, I think the Poisson distribution is the basic thing that underlies football. And you might not be familiar with the Poisson distribution. I'm definitely going to explain a lot about what it is today. But what it's related to is the memorylessness of football. Often when people talk about football, they talk about sort of the build-up of the game, how the game progressed over time and so on, and the sort of feelings and things that happened which sort of led to the picture of the match. That's valuable. But when you actually look at football from a mathematical perspective, you find that it really doesn't have that much memory. That goals can occur at any time during a football match, and they pretty much come at random. They come at random at different rates for different teams, which are better and worse than others, but they pretty much come at random throughout the match. There's a few kind of caveats about that, but that becomes our basic mathematical principle whenever we're modeling anything to do with football. It's the principle that we'll use today for simulating teams and matches, but it's also a principle that we'll use later when it comes to simulating match situations. The whole idea is that you can't see too far into the future in a football match, and that might seem that it makes it sort of random and difficult to predict, but actually the fact that we can't see too far into the future makes it more amenable to mathematics rather than less amenable to mathematics. Okay, I've started off with a few abstract things. I'm going to make it more concrete as we go on about how we're going to use the Poisson distribution. I'll get my screen shared here, and I need to click that. Yeah. So what's the structure today? Well, we're going to look at randomness in football. I've already said a little bit about why football's random. This is a hard concept it's a difficult thing for me to say that football is random. I often say that when I did a lot of interviews around Soccermatics, people ask me how random is football, and I think as a rough rule of thumb, which you can relate to, 2/3 of football is randomness. If you think that there's typically about 3 goals in a football match, 1 goal goes to the better team, and the 2 goals are basically randomly shared between the better team, who might win 3-0, or the other team that might win 2-1. So that's a good way of roughly imagining, for a Premier League match, for example, how the outcome might be described. And the 1 goal is non-random. The 2 goals are random. So it's about 2/3 randoms. I know that in the numbers game, they came up with a half of a football match is random. And there's various studies showing that kind of thing. I don't think you can put an exact number on it, but let's be sure there's lots and lots of randomness in the outcome of football matches, not necessarily in what the players are doing. And that randomness, that leads us to the Poisson model, which is a great description of when a small number of random events occur, and we know there's a small number of goals in football. And then once we have the Poisson model, we're going to then use that to try and find signals for good football. Quite a few questions came up particularly in the first lecture about, I was creating different heat maps and different descriptions of, for example, press, defensive actions, of passing and so on. But what I didn't try in those lectures was to say, well, this thing's good and this thing's bad. And that's because it's really, really difficult to say what's good football and what's bad football. But if there's one way we're going to tease it apart, the Poisson model is the way that we're going to do it. Then I'm going to do a bit of a code walkthrough. I haven't put the link in the YouTube, but if you go into the course webpage, I've put up the link to the new code on the GitHub. which you can definitely sit there and run in parallel to when I'm waffling on. And I've also put the lecture notes for today's lectures. I put a couple more things in since I put them up, but most of the lecture notes for today's lectures are up on the course webpage. If anyone's wondering where that is, maybe someone who knows it can share it in the chat. I've checked that we can have access, so I think you should be able to get into both those things. Code on GitHub, the lecture notes, if you want to have them in parallel. Maybe skip ahead, and if you're getting bored of me talking, skip ahead and see what's coming next in the slides. You can do that as well. I'll have a break 11 to 11:15. Please ask questions in the chat where possible. I will try and remember to break off and answer them on the way. I always say this, I'll take a reasonably slow pace, then I get carried away and start taking a higher pace. But I'll try and take a reasonably slow pace and interact with you along the way. Okay, so when are shots taken in a football match? This is one figure. Now I've actually forgotten which league it was. I think, is it the same as that one? Yeah, it is the same as that one. So it's the Premier League. This is the second half of the Premier League. And this is when, what I've done is I've taken StatsBomb, I've taken the Wyscout data, and I've basically put it into boxes from minute 0 up to minute 48 in Premier League matches for the second half. And I've measured how many shots occur within those minutes. And the main takeaway message here is, if you look at this line, this is the average number of shots throughout the whole match. I've cheated a little bit here. I haven't actually measured the length of all the matches. I've assumed that matches are on average 48 minutes long. If you really want to do this properly, you might want to make an adjustment for that. But this is the average number of shots per minute through, the total number of shots per minute that occurred in all of those matches. The average, of course, needs to be divided by the number of matches. And what you see is just sort of, for the main part, you just see a kind of fluctuation around this average. It isn't that there's 1 minute where all of the action happens. Maybe you can say that in the first minute of the match, in fact, you can say in the first minute of the second half, there's less likely to be shots. Second minute, maybe. But then after that, really up to the final whistle, there's equally likely to be shots in a football match. Now, I think that this is quite surprising when you haven't seen this statistic before, because we do tend to think, and I even think when I'm watching a match, that, well, there's going to be some sort of exciting chance. I have this friend who always talks about like the last big chance. And when we watch football together, he's sitting there waiting, anticipating what he believes is the last big chance that every team always has. And he always says that this will happen in the last 3 or 4 minutes. Then when he's happy, if it's his team who's losing and they need to have this last big chance, when he imagines that this big chance has occurred, maybe in the 46th minute, after that, he gives up all hope. But when you actually look at the stats, there really doesn't exist this last big chance. There is, throughout the match, a relatively even number of shots, apart from maybe in the first minute. Then you can also look at that for the first half and the second half. I was actually quite surprised, because I've done this before and I haven't found this relationship, but I found that there does seem to be a slight difference between the first half and the second half. There are less shots in the first half than there are in the second half. And that might be, I think due to 2 reasons. One is that the matches start slowly. So in exactly this area here, we have, I'm going to put this laser pointer on. In this area here, we have less shots. So when the match starts, the teams come out a bit slower. And then I think there tends to be more extra time in the second half than in the first half. So that's another part of the explanation. But the difference is reasonably small. In the first half, there's around about the same shots as there is in the second half. I think if you were a coach and you were trying to exploit something about this figure, this is what you would think this is what you should be thinking to exploit, because here it seems that there is some chance of getting more shots up. There is no reason, apart from the ball starts in the middle of the pitch, but it does that for a lot of the game. There's no reason that you can't start to have shots, certainly by the second minute in the game. But the overall thing I want to emphasize is that you have this, you could take the first and second half separately, but you have this reasonably, it's a normal distribution of the number of shots that you have per minute, and it's pretty constant throughout the match. And then when we look at goals, we actually find something similar. There are more goals in the first, in this particular data set. There were more goals in the second half than there were in the first half. But they come pretty much any time during a particular half. There's, of course, fluctuations here, and the fluctuations are bigger because the number of events is smaller. But there isn't really a clear pattern where there's an increase in number of goals coming as the match goes on. And neither is in the first half, there's an increase in the number of goals. Again, maybe the first or second minute, there's some pattern. But otherwise, goals can come pretty much any time during a football match. Again, I want to emphasize that if you're working in betting and you want to find a small edge to exploit about this pattern, then there might be something for you to find there. But for nearly all other purposes of modeling football, it's the best assumption is to say that that goals come at any time during a football match, because that's just going to make everything to do with our modeling so much easier. As the Premier League season, I did some other things with it. I did the Bundesliga and La Liga and got similar patterns to this one. The code's in there. We'll have a little look at it later. Okay, so I like to make this figure because I think it brings home the point. So if you divide a match into, let's say, 100 boxes, this is a 100-minute match, a bit longer than we might expect, but imagine you have a 100-minute match. And you say that one box is equal to 1 minute. What you're essentially doing is you're saying that goals occur more or less randomly during a match. And typically, a team scores 1.35 goals, just less than 1.5 goals per match. And you can think about, the way you think about this as a model is you basically think about just throwing these balls, these random goals, down at random inside the boxes. And sometimes you throw for a team, sometimes you throw one ball, sometimes you throw two balls, sometimes you throw three balls, but you'll basically throw these balls down randomly in the time slots, a bit like the time slots I had in the histogram. So you might have 2 goals coming into the match at random points. You might have 1 goal that you've dropped in at random. You might have 2 goals over here. And that's the basic idea of our model. We're dropping goals randomly into boxes. And then we can actually, from there, we can actually build a mathematical description of football. I was asked, for a documentary, I was asked to do this. I was asked to look at what are the chances of Bayern conceding 2 goals in injury time in 1999 in this famous match against Manchester United. I took a couple of statements from the commentators. I rewatched this match and listened to a couple of statements from the commentators. I really like this one. I tell you what, if they could equalize, and I'm not betting against them, I think they'll go on to win it, which I think actually goes against exactly what I've just said. You don't expect, if a team does get that random goal, there's no reason actually to believe more strongly that they'll get the next random goal, other than that they might be a slightly stronger team. And of course, it ends with nobody will ever win the European Cup final more dramatically than this, because Manchester United scored 2 goals in injury time. I'm going to say that they were within 1 minute. They were maybe within 1 minute of playing time, but they were actually within 2 minutes of each other. But for the sake of argument, we'll say that they were within 1 box of my model. And so basically, you can see the match like this. So this Champions League final, you can see the match as sort of a load of empty things. And then suddenly, pop, pop, 2 goals just occurred in the same box in the same minute of this match. And of course, this is very unlikely, that they occur both in this way. But also we watch a lot of football matches. We watch a lot of football matches where different things happen. And now and again, things like this will happen. So the fact that you get these 2 goals at the end of a Champions League final, it doesn't completely dismiss the idea that the goals occur at random. It just happened that in that particular match, it was both of the goals happened in this 99th minute. Again, I think I need to emphasize this over and over again because it's a sort of fundamental thing about mathematical modeling. This is our assumption. It's not that I definitely believe that Manchester United only won the Champions League final because of randomness. It's just that it becomes a reasonable assumption, and very little that we observe in football contradicts that assumption. So for most cases, and even the Champions League final doesn't necessarily contradict that assumption. You can, of course, go in the other extreme. I did this because I thought it was fun. That both goals occur in the same minute or within a minute of playing time of each other. Well, the probability of that is 1 in 100 because I've got 100 boxes that they occur. And if they both occur at the same time, there's a 1 in 100 chance of that. And then that both occur in the second last minute. Well, that's a 1 in a 10,000 chance because you then specify specifically which minute you want to have. You can actually go a little bit further and you can say, well, what if they actually both came from a corner? And then you start to get down to like, this is a 1 in a million chance. So this is a kind of opposite way of seeing it than I've just described, or we see it as random. We actually see what happened and then we calculate the probability of that particular thing happening. I think I want to emphasize this is a just for fun calculation using probability. This, which we've looked at here, is the more serious model of how randomness can fool us in a way, or how we can control randomness. We see football matches as balls falling into boxes, and then we can actually manage to build up a model of those things. So yeah, 1 in a million that they chose. If you'd asked me before the match, to calculate the probability that Manchester United would win with 2 corners within a minute or 2 of each other, I would have probably come up with 1 in a million. But given the amount of football that's played and the different things that can happen, all of those, these different things happen. And I suppose it's the same with the Champions League, with the Liverpool come back from 3 goals down. Liverpool get 3 goals in the second half. A very unlikely event, but consistent with the idea that goals occur randomly in football. So often when we have these very strong stories about what happened in a football match, they often don't lie so far away from the randomness that we expect to occur in football matches. Fun calculation. Oh yeah, I forgot. I put that on there. It's a calculation based on if you ask me before the match, but of course after the match this thing did happen, so it's no longer a 1 in a million chance. It actually happened, so the chance was 100%. But there is serious maths behind it. Oh yes, that we have this, we break things down into boxes, and we're going to put these balls down. And here is the serious maths then. So what's the probability of K goals occurring in a football match? Now, before I was looking at one team and I said there was 1.35 goals. This number 2.7, some leagues it's 2.5, some leagues it's 2.8. It varies a bit, but I think in one Premier League that I was looking at, there was 2.7 goals scored in a match. And I'm going to assign them randomly between 95 minutes, which might be typical for a football match. I haven't looked at, neither of these numbers are absolutely cast in iron, but they're roughly what we see in typical football matches. Okay, so what is the probability of goals? Well, the way we work it out, and it's related to the box model, we see in each of these boxes, what's the probability that it's filled with a ball? So the probability that a particular box is filled with a ball is 2.7 divided by 95. So in this particular